Hi, Dr. Joe Pesce from the National Science Foundation, astrophysicist and program officer. I'm here to answer some of your questions from the James Webb Space Telescope image reveal. Let's start with the first one. So the picture of the stars and gas cloud, isn't every star like our sun or something? So that nice image of the star-forming region contained newly formed stars and stars that were forming. And stars are many different types, and their most important characteristic is their mass. So stars like the sun that have the same mass as the sun are very similar, but stars can have much more mass and much lower mass, and that affects what they look like. So in those images of that gas cloud, the star-forming region, we are seeing stars that are very much lower mass than the sun, lots of stars like our sun, because that's probably the most common type of star, and then stars that have much more mass. That mass will affect how the stars live their lives later on in the future. Okay, so the next question is, please make a video for dummies about light's journey from the Big Bang to our solar system. The Big Bang event, some 13.8 billion years ago, shortly thereafter, photons started flying free through the universe, and at the same time, the universe was expanding from the Big Bang event. So these photons that are traveling at the speed of light are traveling through a universe that is expanding. And that affects them in one fundamental way. A photon of light has a wavelength. We've all learned that the individual wavelength of light gives it its different color in the visible part of the spectrum, and it causes it to be different in other parts of the electromagnetic spectrum. Radio photons have very long wavelengths, and X-ray photons have very short wavelengths. So these are the fundamental characteristics of the photon. All of those photons, as they travel through space, because space is expanding, it's stretching their wavelengths. And by stretching the wavelength gets longer, which causes the photon to become redder, lower energy. And so we call that effect the redshift. So as those photons are traveling through the universe, from the beginning of the universe, or even not so distant part of the universe, they're traveling through a universe that's expanding. It's causing their wavelengths to become longer and the photons to become redder. It's what we call redshift. These, the images that we've seen, are snapshots of past time, correct? And do the objects, do they even exist today? So two things here. Astronomy is a time machine because light takes time to travel and astronomical objects are all very distant from the Earth. So all astronomical objects from the moon out to the very distant regions of the universe, we are seeing those objects as they were in the past. Again, because light takes time to travel from them. When it leaves one of the distant objects that we've seen in the James Webb Space Telescope image release, the cluster of galaxies, for example. The cluster itself is at 4.6 billion light years from us. So that means that we are seeing that cluster as it was 4.6 billion years ago, because it took light 4.6 billion years to travel to us from those objects. So everything we see in astronomy is in fact in the past. I like to call astronomy an astronomical time machine, or a time machine. Do the objects exist today? Because we've seen them in the past, and of course, you know, they're living their lives. Stars in particular go through a life cycle, and so some of the objects that we see in the image release may not exist today. The galaxies probably exist in the cluster image. The individual stars within that galaxy, many of them are no longer around. They have lived their lives over the past 4.6 billion years and have disappeared. Other more nearby objects that we saw from James Webb, for example, the exoplanet image. That exoplanet was just over 1,000 light years from Earth. So that's in our past, of course, the image that we were seeing that was released a couple of weeks ago, 1,000 years in our past. That exoplanet is different today because 1,000 years have passed by, but it's still in existence almost certainly. How much total mass would a gas cloud like the one pictured contain? And this is the Carina Nebula that we saw from the James Webb image release. And that's a big gas cloud. Stars typically form from these big gas clouds. They're called giant molecular clouds, and they have hundreds of times the mass of our sun. And then they're producing hundreds, if not thousands, of stars. The Carina Nebula has some 600 solar masses, 600 times the mass of the sun. We were only seeing a portion of that, but we're probably seeing hundreds of times the mass of the sun in that gas cloud that we saw. And again, remember, that's a very large cloud. It looks like something that we would go out on a summer's day and look up and see the clouds in the sky. But these clouds are very large. They're many, many light years across. And again, they contain hundreds of times the mass of the sun. How long till we see dark matter? Well, this is an interesting question, and it's a very important question because dark matter is an important element of our universe. Dark matter forms the majority of matter in the universe. Matter like us and stars and planets and gas clouds is only a very small fraction of the matter. The largest fraction is dark matter. And yet, we can only see the gravitational effects of dark matter. Dark matter has mass, and because it has mass, it affects gravity. We can't see it in any other way. That is, we can't see it electromagnetically. It's not releasing photons, it's not reflecting photons, and so we only know about it because of its mass. Now, we have speculated what makes up dark matter. Subatomic particles or other exotic things. And astrophysicists and particle physicists are looking to try to figure out what makes up dark matter. This is a very difficult study to do because the dark matter particles are very weakly interacting with other objects in the universe apart from their gravity. So that makes their detection very difficult. I would guess, this is my opinion, that we will in the next 20 or 30 years, and maybe on the nearer term, detect dark matter probably in our particle accelerators. There are ongoing experiments to look for dark matter, and I fully expect that we will find the dark matter particle in the near term. So I don't know exactly how long it'll be. The studies are underway, but we will detect dark matter at some point. Does JWST or other telescopes, do they have any role in hunting potentially Earth-killing asteroids? Or is James WST only useful objects further out in the universe? No, indeed, JWST can observe objects in our solar system. There have been recently released images of Jupiter from the James Webb Space Telescope. But more to the point of potentially Earth-impacting asteroids, James Webb can certainly observe them. Now, these objects are very small, so it's unlikely that observations from the James Webb Space Telescope will be able to resolve them, that is, to see what they look like. But by studying the asteroid's light, we can determine what the composition is, if it's rotating, what the density of the object is, and what the potential impact is if this asteroid were to affect Earth in any way. So James Webb does certainly play a role, and there are many other telescopes that are playing a role in detecting and characterizing dangerous near-Earth orbiting asteroids.